So
Start
wait
the
for.
class.
Okay. Good morning, students. So welcome back to our states of matter, gases and liquids, part 3. So my name is Priyadarshini. Okay. So in the last class, we have discussed about the ideal gas equation. We have derived the ideal gas equation from all the gas laws. So prominently the important points of the last class were the laws, gas laws. Those were Boyle's law, Charles law, Gay-Lussac's law, Avogadro's law, and from that we have derived uh, ideal gas equation. So that derivation is also a 4 mark question. Okay, that slide where from all those 4 laws we have derived ideal gas equation is also an important 4 mark question. Okay, so now what are ideal gases and what are real gases? So there is another concept called as real gases. Okay, ideal gas and real gas. All the gases, any gas, all the gases which follow those laws. Which laws? The gas laws. Boyle's law, Charles law, Avogadro's law. If gases follow those laws, then that gas is a ideal gas. Okay, if they do not follow these laws, then those gases are called as real gases. Okay, or so we do many processes in our daily life, even in experiments. Okay, so do these gases we are dealing with, are they real gases or ideal gases? All of them are real gases. Okay, so why we consider them as real gases? So for example, see this equation, PV is equal to nRT. Okay, this PV is equal to nRT is derived from the gas laws. So if we plot a graph, if we plot a graph for any process, for example for Boyle's law, PV directional, PV P proportional to 1 by V, then exactly the curve which we have drawn theoretically, we have seen in the last class, has to be obtained. But is it really happens? No, that does not happen. The plot will be, the curve will be deviated. Okay, the same curve will not be obtained. There will be a curve, but what we thought, what we'd have drawn theoretically will not be obtained. There will be a slightly deviation from the curve, means there is a deviation from the ideal behavior. They will follow the gas laws, but there will be some deviation for the actual gases. Okay, so the actual processes, actual gases are called as real gases. Okay, they are called as real gases because they will deviate from the ideal behavior, and that really happens actually. So that's why they are called as real gases. Okay, so a gas that follows Boyle's law, Charles law, and all the laws are called as ideal gases. Such a gas is hypothetical. Hypothetical means imaginary. Okay, so real gas can be can behave as ideal gas at certain temperature and pressure conditions only. Means at low pressures and medium temperatures or high temperatures, then real gases behave as ideal gases. Okay, it is assumed that intermolecular forces are not present between the molecules of an ideal gas. So we have derived the PV is equal to nRT, PV is equal to nRT ideal gas equation, assuming that there are no intermolecular forces. Not we have derived. So the scientists have given that equation, PV is equal to nRT, after many experiments for ideal gases, assuming that intermolecular forces are not present between the molecules. Is it real that there is no intermolecular forces, students? So in the first class itself, we have discussed about intermolecular forces. There will be intermolecular forces between the gases, molecules or atoms. Okay, there will be intermolecular forces. We can minimize the intermolecular forces. We can minimize the intermolecular forces at low pressures and high temperatures. So that is the situation. So then if we can minimize the intermolecular forces, then the real gas becomes an ideal gas. So that's the concept. Okay, real gases follow these laws only under certain specific conditions. Okay, in all other situations they deviate from ideal behavior. What are the differences? Simple. So ideal gases obey all the gas laws under all conditions and temperatures. So but that is a hypothetical situation. There will be no ideal gas actually. Okay, so the real gas obeys at low pressures and high temperatures. The volume occupied by the molecules is negligible as compared to the total volume occupied by the gas. Okay, so here it tells that volume occupied by the molecules is negligible, means they are occupying very minimal volume. So here the volume occupied by the molecules is not negligible, and the forces of attractions among the molecules are negligible. So what we have discussed in this third point, intermolecular forces are not present. But for real gases, actually the forces of attractions are not negligible at all temperatures or pressures. And the actual equation, this equation shows you the completely shows you the behavior of ideal gas, that is PV is equal to nRT. Then what about the real gas equation? So this is the real gas equation. You have to remember, this is one of the important 2 mark question. Okay, so that real gas equation is also called as van der Waals equation. Okay, van der Waals equation. What is van der Waals equation? P plus a n square by v into v minus nb is equal to nRT. Is there any resemblance, students, in these two? Is there any resemblance, similarity in the? Yes. P. So there is P and there is V, but something is added to P here and something is substituted in V and same nRT. Okay. So these are nothing but corrections. Pressure and volume correction means in this equation, no, after decreasing there will be some corrections will be there. Decrease is there, some volume correction is there. So that's why some corrections are taken and included in the equation which comes under van der Waals equation. Okay, so this very simple. Ideal gas, there are no intermolecular forces. Just to show it in the pictorial form. Ideal gas equation, there are no intermolecular forces. Real gas, for real gas, there are, for a particular molecule on a particular molecule, there are different forces of attractions from different molecules. Okay, so there is the equation including this PV is equal to nRT. We are going to include this equation. Okay, so how can you calculate this equation? From PV is equal to nRT equation. That is the derivation here. Very simple. PV is equal to nRT is rearranged in this format. Okay, so this is PV is equal to nRT only, but we have rearranged. PV, if V goes this side, that is PV, RT goes near N, that will be nRT. Okay, so we have rearranged like this. N by V, replacing N, what is N, students? What is N? N is number of moles. Number of moles of any gas is equal to mass by molecular weight of that gas. Means m by small, mass means small m, molecular weight is capital M. So if you write m by n in this equation, m small m by capital M by V, the same V is equal to P by RT. So m by V, this m by V, small m by V is equal to D by capital M by RT. So density is equal to DRT by P. Sorry, density is equal to molecular weight is equal to DRT by P. If you consider density only, if you want to calculate density, then M goes here, MP by RT. So this is the equation. So at our level, we simply get some equations from this equation. If questions are given and all the equations are given and asked to calculate weight, you have to take this equation. Okay, if density is increased or density is asked to calculate, this equation you take, m goes equal to p by rt. Okay, coming to another concept, Dalton's law of partial pressure. So what this law says, again this is another law of gases. Dalton's law of partial pressure means nothing but total pressure exerted by the mixture of non-reactive gases is equal to the sum of partial pressures of individual gases. So there is no explanation for this definition. The definition itself gives you the clear picture. You understood? Okay. So don't think that I'm reading the definition. The definition itself gives you the clear picture. Okay. See here, non-reactive gases, we have taken A gas, B gas, C gas in a different containers. Okay, three different containers. Then what is the pressure exerted by A gas on the walls of the container? So imagine, pressure of any gas means, pressure of any gas means pressure exerted by the gas on the walls of the container. For example, if you push something on the wall with your hand, okay, that is the pressure exerted by you on the wall. If all the gases move randomly, the gas particles will collide in the walls of the container, so that pressure is exerted on the walls of the container. That is the pressure of the gas. Now that is the partial pressure of the gas. Partial pressure, when a single gas is there, we do not consider it as a partial pressure. Okay, whenever a single gas is there in a container, we do not consider it as a partial pressure. We simply consider it as pressure of a gas. Then when do we consider the partial pressure? We consider partial pressure for a gas when it is present with some other gas in a container. Okay, means partial pressure is the individual pressure of the gas when it is present with some other gas molecules. Understood? Okay, now coming back. So this is the pressure of A gas. So here there is a pressure of B, that is PB. There is some pressure by C, we call it as PC. The same number of gases are taken in a single container. Okay, all these gases are poured into some container with same volume. Now gas A, gas B, gas C have taken in the same container. What is the total pressure? P total is equal to this PA plus PB, PC. Don't think that pressures will change. So that is nothing but Dalton's law. What he is saying, that pressure, total pressure is equal to partial pressures of A gas, B gas, C gas. Now here comes the concept of partial pressure. So partial pressure is the individual pressure of each gas when it is present in the mixture of gases who are non-reacting. Okay, so so here we have taken like this: P total is equal to P1, P2, P3, whatever, when whichever the number you can take like this. That is equal to summation of all the gases pressure, summation of pressures of all the gases. Okay, so here you can take another, suppose A gas has 4 atmospheric pressure, B gas again 4, and the total pressure when these two are taken into a single container, then 4 plus 4 8. Okay, so where should we apply this Dalton's law? Is it useful? Yes, that we are taking two applications of Dalton's law of partial pressures. Okay, so here, one of the application is we are going to calculate the pressure of dry gas. Okay, so that is one important application of Dalton's law of partial pressures. So here the definition is given: the pressure exerted by an individual gas in a mixture is known as partial pressure. Another definition you have to know, that is aqueous tension. So aqueous tension. See, aqueous tension means the pressure due to water vapor is known as aqueous tension. Water vapor pressure. What is water vapor pressure? Suppose if you take, suppose consider this beaker. There is an inverted tube here. Then definitely some water go into this tube due to capillary action. Okay, consider only water is there here. Now some of the water molecules from the surface go into the vapor state. Even we do not heat, also water evaporates. Is it really true? Water evaporates without heating? Yes, at room temperature also water evaporates. That is the daily criteria that we are looking in experiencing in our daily life. If you put water in a container outside, even if you put water on the floor, after some time that will be dried, because water evaporates at that temperature also, any temperature. But the time taken is will be differed. So some of the gas molecules will evaporate into this container, into this tube. Okay, after evaporating, that is nothing but water vapor. It is nothing but gas. That gas also exerts some pressure on the container, on the walls of on the walls here. So now that, whose pressure is it? It is the pressure of the water vapor by this water. From this water, water is evaporated, water vapor is created. Water vapor is nothing but gas. That gas will exert the pressure on the walls of the container. That is nothing but aqueous tension. Okay, tension is nothing but pressure here. Aqueous, water tension, water pressure, aqueous pressure. Okay, aqueous tension. So now how it is useful to calculate the pressure of dry gas. Then what is the pressure of dry gas? See here some reaction is going on, some reaction is going on, and for example hydrogen is evolved from this reaction. Hydrogen is lighter than this water, so be it will be going upwards in this tube. Okay, so whatever any gas, some reaction is going on, that gas is collected in this container over the water. Okay, so here see the yellow color thing, yellow color. So the tube is also given as yellow color, means the gas is coming out, and see bubbles of the gas is going upwards, and that gas is collected here, collected here. Okay, this, the scientists may require this gas, so this gas is collected in this inverted tube. Now then what is the pressure created by this gas? Okay, so this gas is considered as moist gas now. Why? So this gas includes dry gas plus water vapor, because already there is water. Okay, already there is water. So this water vapor as well as dry gas means coming from this reaction. The gas coming from this reaction is considered as dry gas. Okay, so now the total gas is a mixture of dry gas as well as water vapor. So the total pressure the is equal to addition of dry gas pressure plus aqueous tension or water vapor pressure. So now it is called as pressure of moist gas. Okay, so that moist gas pressure is equal to dry gas pressure plus aqueous tension. Now what is the pressure of dry gas? Moist gas pressure minus aqueous tension. Okay, so what is the way of calculating this dry gas pressure? Means if you want to know the even weight, what is the weight of the gas released, and how many molecules of gas is released, what is the volume of gas is released, so we can easily measure if we know the pressure. Okay, means what is the pressure of the gas released from this container, means from this reaction. Okay, that is the application. So simply, gas which do not react with water are usually collected by downward displacement of the water and is collected over the water. The pressure exerted by the gas due to gas is due to gas collected and water vapor. Okay, total pressure is equal to the dry gas plus water vapor pressure. Understood? Okay, next, calculations of partial pressures. So as we have discussed, total pressure in a gaseous mixture is the sum of partial pressures. So this is also important question for 4 mark, but it's very easy to calculate. All the questions from this chapter are very easy. You are going to get 4 plus 2 means one 4 mark question and one 2 mark question. Okay, but this is the scoring topic, I can say, because there are, if you see this slide, it looks like difficult, but it is very easy to derive this equation. It is very easy to remember also. If you once write on paper, then it will be easy. If you see with your eyes like this and try to remember, definitely you are not going to remember even one equation also. Okay, unless and until if you see repeatedly, like PV is equal to nRT taken in a bold font, so you can remember that equation. But these derivations you can't remember by looking at the equation, or simply by chatting and looking on the equation you can't remember, you will going to lose any class. Okay, so just write on paper whatever you want to write in an exam. First you have to produce that on the paper, put it on paper, then you can understand what mistakes you are going to do in exam. So you feel that you know the answer, but while writing you feel difficult to put it on paper or present on paper. Okay, so if you don't know what is the problem, then if you want to experience the same thing and if you want to rectify that mistake, first put it on paper yourself before the exam. Means now itself, today itself or tomorrow. Then if you put it on paper, those equations or any answer, even English also, you have to write to remember it well, very well. Okay, then what happens, you can understand the you can understand what mistake you are going to do in the exam, and so that you can rectify now itself. So especially chemistry, physics or maths, definitely you have to write it on paper. If it is botany, zoology, you have to draw the diagrams on paper before the exam. Okay, so coming to the calculation of partial pressure. So what we have discussed in Dalton's law of partial pressure, P total is equal to P1 plus P2 plus P3 summation. Okay, what is PV is equal to nRT from the ideal gas equation. So see the ideal gas equation, PV is equal to nRT. So for gas A, consider this ideal gas equation for gas A, gas B, and gas C. Okay. Now PA is equal to V. So the same volumes we have taken now. Same volume we have taken. So volume will remain constant, but number of moles of gases are different. Okay, number of moles of gases are taken difference, means number of molecules are different. So P A into V is equal to NaRT. R is ideal gas constant. T is means temperature, at what temperature we are doing this experiment, that's it. So temperature is also constant. So Pa, if you rearrange this equation for A gas, Pa is equal to Na into RT by V. PB is equal to NBR. So this is the condition. Then what is the total pressure P? Total pressure P is equal to PA plus PB plus PC. Thus that's why all these formulas come together. P total P is equal to Na, like this we have taken. Now RT by V is constant, common uh, in all these. So that's why P is equal to RT by B into Na plus Nb plus Nc. Means Na plus Nb plus Nc is nothing but total number of moles of gas in a container. Total number of moles of gas in a container. Okay. So here we are equating partial pressure of A to the total pressure. Okay, partial pressure of A to the total pressure. So what is our intention? What is our intention is, we are going to calculate the partial pressure of one gas. Okay, if we know the total pressure. Understood? So there is a reaction, there is some reaction going on in that three gases are there or two gases are there. Okay, two gases are there, and the total pressure we know, we can calculate easily. There are instruments to calculate the total pressure of the gas. Okay, then what is the partial pressure of A gas and B gas? So that is our intention for deriving this. So now we are equating PA to PB. So PA by PB, PA means you can take A or B or C, means partial pressures. So partial pressure of A by the total pressure is equal to Na by Na into RT by B. So this we have taken this by this. Okay. So PA by PB is equal to all this RT by V. RT by V is cancelled. Na by Na plus Nb plus Nc. So what is this Na by Na plus Nb plus Nc? Have you studied about mole fraction, students? Mole fraction. Have you studied? Or have you heard of mole fraction? I think yes. Okay. Mole fraction is number of moles of a substance to the total number of moles of the mixture. Okay. So for example, there are, for example, see here, mole fraction of A. So it is given as chi A, chi. It is a symbol for chi, but here we have taken x, simply xa. It should be chi A. Okay, xa. You can write like this also. This symbol, it gives you the representation for moles, mole fraction of A. Mole fraction means simply fraction of A substance to the total, simply like percentage. Okay, percentage of chemistry marks in your total marks. If your total marks are total subject marks are 100, means including, suppose if you are MPC students, maths, physics and chemistry combinedly you got only 100 marks. Okay, and your chemistry marks are 20. What is the marks fraction? What is the marks fraction of chemistry? So simply chemistry marks by total marks. What is the percentage of chemistry? What you will do? Chemistry marks by total marks you have got into 100. If 100 is not taken, it will become fraction. If 100 is taken, it will become percentage. Simply, mole fraction is moles of one single substance by total number of moles of all the substances. Okay, that is. So nothing but, if suppose this box, if you consider there are two substances in a mixture, then mole fraction of A is equal to number of moles of A by total number of moles, that is Na plus Nb. So mole fraction of B is equal to number of moles of B by total number of moles of A and B. Okay, so now pa by p, so partial pressure of A by partial pressure of P is equal to Na by total number of moles of, so this will give you the mole fraction of A. So simply partial pressure of A by P is equal to mole fraction of A. So you can rearrange this. Partial pressure of A is equal to mole fraction of A into total pressure. Similarly, you can write partial pressure of B is equal to mole fraction of B into P, and similarly the same thing for partial pressure of C. Okay. So next law called as Graham's law of diffusion. Okay. So first of all, what is diffusion? What is diffusion? So diffusion is a process in which gases molecules spread out and occupy the volume of the total container. So simple, you all experience this in your daily life. If you spray any perfume from the one corner of the room, that perfume will spread throughout the room. So simply the fragrance of perfume spread because of this property. So diffusion is a process in which gases molecules spread throughout the container and occupy the total volume. So that is nothing but diffusion. You can see here. So initially the some gas is sprayed here. Then later it will occupy the total container like this. Initially there is only, the gas is only at this position, but after some time the gas is spreading throughout this container. Okay, so the simple thing here, lighter gases diffuse more rapidly than lower gases. Okay, what this law state, Graham's law of diffusion, what this law states the rate of diffusion of a given mass of a gas is inversely proportional to the square root of its density. Okay, so it is not simple as we are saying like this. So this is proposed after many experiments. Okay, so what is the rate of diffusion, at what rate that gas is diffused is taken in relation with the density. How it is released? Rate is inversely proportional to the square root of density. Okay, so in this note I want to say you about effusion also. So both looks like similar definitions, but there is some difference here. Diffusion is shown in this picture, but effusion is shown in this picture. Effusion is the process by which a gas escapes through a pinhole into vacuum. So earlier there is no gas here, but due to high pressure of the gas that is taken initially here, it is gone through this pinhole. Okay, from here to here, like this. Okay, gases molecules coming out of the perfume bottle. You can simply imagine gases molecules coming out of the perfume bottle. Okay, they are coming out of a pinhole, so you can consider that as effusion. But after coming out, spreading throughout the container is considered as diffusion. Okay, so here effusion is unidirectional, means if the gases are coming from this pinhole, they go in the single direction straight away. But diffusion, there is no direction for these gases molecule, they will diffuse in throughout the in all the directions. Okay, so this is the rate of diffusion is inversely proportional to the density. So we have some derivations, means for different gases, for R1, R1 and R2 is nothing but rates of diffusions of different gases. Okay, so we are taking different gases and we are taking these rates of diffusions in terms of time taken to diffuse, density, molecular weight. Okay, so these are useful to calculate. Practically there are a lot of applications practically, but as we are studying in the intermediate level, we are just studying this to apply this in future. But as of now, these are helpful to solve some problems only for you. Okay, but everything has many applications, not very simple. We have taken on the slide, we are reading this and that's it. Okay, we are calculating, not like that. There are a lot of applications practically. Okay, so R1 is equal to, you can we are removing the proportional here, so proportionality constant is taken. R1 is equal to K square root of 1 by D1. So this is taken for R1, means for one gas. Next R2 means another gas. What is R and rate of diffusion. Rate of diffusion of any gas is equal to volume of the gas diffused by total time taken for the diffusion. Okay, rate means rate, speed or velocity. Okay, so simply velocity means distance covered in a unit time, isn't it? Like that, rate of diffusion means volume of the gas diffused by the time of diffusion. Okay, this particular thing is directly proportional to 1 by square root d, or simply inversely proportional to square root of d. Okay, so the here we have taken for two gases, so R1 by R2 is equal to inversely proportional, so that D2 by square root of D2 by D1. So we can take that in terms of molecular weight also. So molecular weight and density also. So molecular weight is equal to 2 into vapor density. So therefore M, molecular weight, is equal to 2 into density. Okay, so density is equal to m by 2. So here density is there. If you want to include molecular weight in this, if you want to replace this density by molecular weight, that will become R1 by R2 is equal to m2 by m1. So we can also take in terms of time for diffusion. So rate of diffusion is inversely proportional to time taken. From this equation, R is equal to V by T. If a same volume of gas is taken for two different gases, same volume of gas is taken for two different gases. So what is the difference for these two gases? There is a difference of weight and molecular weight, but the volume is taken same. Okay, so R1 by R2 is equal to, from this equation, V by T, V by T1 by V by T2. Okay, so that will become equal to R1 by R2 is equal to T2. This T2 goes upwards in the numerator and T1 goes to denominator portion. So R1 by R2 is equal to T2 by T1. That will be equal to square root of D2 by D1. That is equal to M2 by M1, square root of M2 by M1. Okay, so these are helpful for you to calculate some problems given. Okay, next, theory, kinetic molecular theory of gases. This is very important question for your IPE point of view, 4 mark question. Okay, so there is, it looks very simple, this but these postulates are given after many experiments. The same thing I'm saying. This looks very simple, but not easy to this is obtained not easily. Okay, so very easy answer. This is very easy answer for you students. You can study these points and you can represent these points, same points on the paper. You'll get 4 marks. So what the scientists have thought? Okay, we have derived all the gas laws. Uh, what we have discussed in the earlier class, gas laws. All these gas laws are uh, bulk properties, bulk of the system. But what is happening in the molecular level? What is happening to the gases? But are gas is not a large molecule. Gases means there are number of particles of, means atoms and molecules are there. What is going in the microscopic level? That interest is taken by Boltzmann, Maxwell and Clausius. Okay, they have proposed this kinetic molecular theory on gases. What this law says, so it is simply read out the postulates, you can understand the lines very easily. Okay, so gas is composed of particles which are in constant motion. Okay, gas particles move and composed of particles means here they may be atoms or molecules. And the next postulate tells you that, so if some gas is taken in a room, that same gas is taken in a beaker, 100 ml or 200 ml of beaker, it acquires the volume of the container. So the same 100 ml gas taken in the 100 ml beaker, if you spread out in the room, what happens? It acquires the total room volume. Means the space occupied by that actual space occupied by the molecules of the gas is very less compared to the total volume. Okay, so that is the next postulate. Okay, and the third postulate tells you that the individual particles neither attract or repel one another. Actually this is not true. If that is an ideal gas, then only it is true. So all the theories, so the name itself indicates that it is a theory. So according to this theory, they proposed, they assumed that individual particles neither attract or repel. Okay, assuming this line only, all the gas laws are derived. Okay, so what they thought is, all the gas laws, result of all the gas laws is because that all those scientists who have proposed, they assumed that individual gas particles neither attract nor repel, means there are no intermolecular forces. Okay, and whenever the gas molecules are moving here and there, definitely there will be a collision. Okay, so all these collisions are elastic collisions. Elastic collisions means, so the energy, whenever two balls or two molecules or two atoms are collide, their energy their energy may be exchanged between the two particles or two molecules. If collision takes place, energy may be exchanged between those two, but energy will not be lost. Whenever particles collide with one another, they bounce rather than they stick. These collisions are elastic. If one particle gains kinetic energy, another particle loses kinetic energy. So the average remains constant. There is no loss of energy. There is no loss of energy. Loss of energy means loss of energy in the form of some heat or anything. Okay, energy will be lost and gained, but energy is not lost completely. So the average remains the constant. And the last postulate is, the average kinetic energy of the molecules is directly proportional to the absolute temperature, means temperature in kelvins. Okay, so deduction of gas laws from kinetic gas equation. What is kinetic gas equation? First thing, kinetic gas equation is PV is equal to 1 by 3 mnc square. C is the velocity of the gas. Okay, velocity of the gas. Velocity of the gas means all the gases do, all the particles of the gas has the same velocity, students. So in a room we have taken, suppose 1 mole of gas. 1 mole of gas means 6.023 into 10 power 23 gases particles are there. All the gas particles have the same velocity? No, definitely not. There will be different velocities for different gases. So we will take the average velocity. So here We have different kinds of velocities, but here we have taken only c square, means root mean square velocity. Simply average velocity, consider it as average velocity of the gases particles are taken. C means here velocity. Okay. Okay. PV is equal to 1 by 3 mnc square. So from this kinetic gas equation, we can deduce all the Boyle's law. So these, for example, this particular slide will be asked for a 4 mark question. Means deduce Boyle's law and Charles law from kinetic gas equation. So that is the thing. So from this, how you can deduce means at constant temperature, the volume of a gas is inversely proportional to the pressure. That is nothing but Boyle's law. So PV is equal to, so rearrange the equation like this: 1 by 3, multiply and divide this 1 by 3 with 2. Okay, so 2 by 2, numerator 1 to denominator 1 2. Okay, so from this, you can separate 1 by 2 mnc square. So what is this 1 by 2 mnc square? It is nothing but kinetic energy. Students, what is kinetic energy? Ke kinetic energy is equal to 1 by 2 mv square. You have studied, you might have studied that in physics also. Kinetic energy is equal to 1 by 2 mv square. The same thing here, mv square. This is c is nothing but velocity, means velocity of the gases particles. So c square is nothing but velocity square n. N means if there is 1 mole of gas, this will become 1. If n number of moles are there, then we to take n square. So this 1 by 2 mnc square is directly proportional to the temperature. That is nothing but kinetic energy is directly proportional to temperature, which is nothing but the last postulate of our, see here, kinetic gas, molecular theory of gases, kinetic energy is directly proportional to temperature, last postulate. So here 1 by 2 mnc square is directly proportional to temperature, which is nothing but kinetic energy. So here kt is taken, one proportionality constant is taken. So PV is equal to this, in the place of 1 by 2 mnc square, you can write KT. K is proportionality constant here. T is at a constant temperature, because this is a Boyle's law. This is Boyle's law. So KT we have taken. So PV is equal to 2 by 3 this KT. Understood? PV is equal to 2 by 3. In this 1 by 2 mnc square, we can write KT. So nothing, PV is equal to 2 by 3 KT. No, so now this 2 by 3 and K and T all are constant. Yes or no? 2 by 3 is a digit, so it is a constant value. K is the proportionality constant derived from here, and T is the temperature. Temperature itself is constant in the Boyle's law. At constant temperature, the process is taking place. So PV is equal to total, this is constant. So PV is equal to constant. So what is PV is equal to constant? It is nothing but Boyle's law. So that's how we are relating, simply relating gas laws to the kinetic gas equation. So we can also draw gas laws from kinetic gas equation. So after proposing all the gas law, this kinetic theory of gases is proposed. Okay. So after proposing this theory, these scientists have related, they proved that their theory is correct by deducing all the gas laws. Understood? So the same thing, Charles law is also derived in this manner only. So PV is equal to 2 by 3 KT. So which is constant in Charles law? Pressure is constant. So V by T is taken this side. The same equation derived here. V by T is taken and pressure is taken this side. So V by T is equal to 2 by 3 K by P. So which is nothing but all these terms are pressure constant. 2 by 3 is constant, K is proportionality constant, P is constant in Charles law. So V by T is equal to constant. So this is how Charles law is deduced. So Avogadro's law is also deduced in the same manner. So here for first gas, PV is equal to 1 by 3 M1 m1 n1 c1 square is taken. So what is Avogadro's law? In Avogadro's law, P and V are constant. Oh, no, no. P is constant. Equal volumes of all gases occupy same number of moles kada. So equal volumes are taken. So PV is equal to 1 by 3 m1 n1 c1 square. For second gas, the same thing. So they have equated P and V, so the same pressure and same volume is taken. So m1 n1 c1 square is equal to m2 n2 c2 square. Okay, so here also half is got cancelled. Mc square is equal to m2 c2 square. Okay, so from this and this, if m1 and c1 is same, definitely n1 and n2 is will also be same. Understood? So from this equation, average kinetic energy per molecule is same for both the gases, as both the gases are at the same temperature. From, okay, so this line is again taken from the last postulate of kinetic theory of gases. Okay, 1 by 2 m1 c2 c1 square, this is nothing but kinetic energy. So average kinetic energy of gas 1 is equal to average kinetic energy of the gas 2, because both are taken at the same temperature. Okay, if these two terms are same, then similarly here in between n1 and n2 are there, these two will also become equal. Okay, so n1 and n2 is also equal. So coming to Dalton's law of partial pressure. So coming to Dalton's law of partial pressure, so P1 is equal to 1 by 3 m. So PV is equal to 1 by 3 m1 n1 c1 square. The equation, so rearrange equation is rearranged here like this. Oh, it's cut from somewhere. So
Madam, can you close the session?
okay, sir. Okay, students. I'll continue in the next class. What you do is try to try to put all these derivations on paper, so that you will understand completely. Okay, listening once may not may not print this information in your mind. Just put it on paper, so that it will be easy for you in the next class. Okay, thank you students for watching.